All right, welcome to the last year. We are very happy to have our own participants.
Thank you for the introduction. I know it's the last day of the semester, so it's but today I'm going to tell you a little bit about some results in pseudorandomness, and this is going to work with Paredes, who is my advisor at CU, and then Rafael Cerverio, Professor at Columbia. For those that don't know me, I lecture here in Princeton. I semester, and yeah, and so my goal for today is to tell you about a couple of results, but I want to, this is going to be the outline. I want to kind of move through the results a little bit first by kind of telling you about what pseudorandomness is. I assume that a lot of you all already are familiar with pseudorandomness and why it's important, but I still want to add a little bit. Then I'm going to tell you about one of the most, not most, but one of the many great highlights of randomness is this notion of bound independence. I was using different things, and this is kind of one of the inspirations to the work that I'm going to present. And then I'm going to show you a kind of general framework to what we're doing and kind of explain what we're doing and why you should care about this type of work. And then I'm going to tell you a little bit about how this is going to have two parts: one about reducing error and so on about constructing an optimal cap analysis. Okay. So I want to start by motivating like pseudorandomness, and this is going to be very, very general and basic section. So in pseudorandomness, our main goal is when we have maybe some algorithm or maybe some source of randomness, and we want to produce a bigger source of randomness so that we can, for example, convert a random algorithm, so an algorithm that uses randomness, which is a probabilistic argument, to a deterministic one that has a similar time. So an example of this is we can be, if we have an algorithm that works with a certain probability and requires tossing a bunch of different points, our goal is to try to convert them by removing the randomness. And there's a lot of very famous results that kind of follow this strategy. Ransom is one that for the last years where we tried to someone showed that given a number of determining whether it's a prime or not problem. Another like big problem that is kind of related to this problem now, which applies to predictability. So if you have graphs and you want to determine whether that graph is connected in logarithmic space, you can just based on randomized log space of it. But a second motivation to do this kind of thing, for those that are not really into complexity or maybe not into pseudorandomness as a thing, this might be a more interesting motivation, which is to construct explicit objects whose existence is only guaranteed by probabilistic. Let's say you prove the existence of something by probabilistic arguments, but you also want to efficiently construct the instance of this object. So an example of this is graphs. There's a lot of literature on these kind of graphs, but one example is that if we sample the uniformly random regular graph, we could disclose a very expensive graph, and we want to randomize this. Another example is coding theory, and I'll also mention some of the connections. We know that a random is good for whatever definition is good, but we want to construct explicit, deterministic codes so that you can actually. So if you, and I'll mention some more like results of this kind of talk, but this is another reason for you to care about surveillance. If I have like using argument, and you want to construct an algorithm that design an efficient algorithm that okay, so the key kind of character or the key thing that is in pseudorandomness is this notion of a pseudorandom generator. And I know there's a lot of text here, and then also motivates. So the idea is that we want to produce a function g, like this g, which is a function from 0 bits to 0 bits, but from t bits to n bits, where n is going to be the larger t, And we're going to say that this function epsilon pools a family of tests, where a test is just a function that takes all those bits and like gives us a signal 0 or 1. It's to say that the function or pseudorandom generator is not function if the probability when we run this the f function with the uniformly stacked sequence of bits, or when we run it with a small uniform sequence and then apply key bits, the difference between this. But this is very hard to parse. I don't know about. The idea is that usually if we have n random bits over here, and use this to feed the f and produce some zero outputs. And we, average all the elements, all the results. And what we want to do is we want to simulate this procedure, but with less bits. So if we have a pseudorandom generator G that given an input t bits, where t is a smaller number, and this pseudorandom generator will produce a bigger sequence of t of n bits that will look uniform, so that when we feed these n bits to our function f, we still want it to have kind of the same behavior as if we use the purely uniform n. So that's why I'm just like, right, this is like this approximately equal out to root by factors. This is the notion of the pseudorandom generator. Given some family of functions that do certain things, we're going to fool these functions by, instead of using a pure source of n bits, we're going to use a smaller source of bits, and then use our pseudorandom generator to kind of fool this function. It's using uniform bits. And just a couple of points of application. Whenever I say like x until the implicit n, this I mean that I'm sampling the x from uniform, a set of uniform sequences of x. And so for here, I mean we're sampling C from a sequence of T uniform bits, applying G to C, and it's the same thing as this. Okay. So this is the kind of setup if we work with randomness. And now we can think about how we can actually produce these generators and what kinds of things we might. And before I move on, just I'll have these like boxes that are running certain things. This value t over here, we also call it the C length. So it's whatever we need to provide C to our and if we're the C length of our original kind of procedure of like taking n bits and then providing it to f, and it's between bits. But when we use our pseudorandom generator G, the C length is t because we need t bits to kind of jumpstart this. So the C length is kind of the number of bits, random actual uniform bits, kind of provide to our okay. So here's an example of a green pseudorandom generator. Suppose we have a polynomial time computable function that we can, so in this case PRG, that we can use a polynomial time that has C length O of log n. So it goes from log n bits and kind of amplifies the n bits, such that it 0.1 fools all functions that are computable by circuits that have size of 20. So if you're able to do this, then you'll be able to prove things like people. So all the algorithms that you can, all the problems that are solved with the probabilistic are also solved with the deterministic problem. You'd also be able to convert any proof that is checkable in polynomial time to explicit construction. So thing I was mentioning before. So this would be in PRG, and obviously this we don't know about this because if we did, I wouldn't stop. This would be pointless. Kind of all these different things. But so the idea here is that if you have this PRGB that can kind of expand from like log n bits to like n bits, then you could have this procedure to, for example, show that people. So if you have an algorithm that, let's say that f instead of being a function is an algorithm that says accepts or rejects and feeds n bits of randomness in order to work. If we can fool this function like well enough, then you can sort of run it with our PRG and then try all possible C's and look at all the outputs that our function will compute after we apply the PRG, and then look at all the outputs and take those. And you know that if our function f is good enough, so if our algorithm is accepting, then this majority will also give us the actual answer within the choice. And since the C length, so the number of bits we use is log n, if we enumerate through all of them, this is a poly n time, or the number of those sequences is poly n, so this is a polynomial time. Okay, so clearly this dream PRG is a little bit too much to look for. So what kinds of families of functions do we instead look at that are more amenable to PRGs? And this is where bounded independence will show up. So now let's suppose that we're going to look at functions that consist or families of k-wise independent tests. So we want functions that only look at most k bits of the setup as we have. If we have, if our input is n bits, we want to only consider functions that produce an output, but they only inspect at most k of the bits of our input. And this is what we mean by k-wise independence. And the way to think about that is that these functions work if our distribution over bits is k-wise independent. Any sets of k elements, any set of k elements, k indices of our sequence of bits will look different. So this was kind of a big idea that people had in pseudorandomness. This is a very old idea that for a lot of cases, if we don't need to, for a lot of applications, we actually don't need to look at a lot of the bits. So an example of something that would look like this is if you have some sort of probabilistic method to show the existence of something, where like you have a big object, but wants to, for example, the existence of like a small thing. So if you think about like Ramsey theory style results, if you have, if you can prove that, like an example case is something like I want to show that there are graphs that Ramsey theory results in the style you want to either have the existence of a large enough clique or a large enough set, and this large enough will feel around the size log n, and so you kind of given a graph to test whether or not there's a clique of size log n, you only have to look at log n bits at the same. So all the functions that we need in order to test whether or not there's a clique of size log n are tests that only look at k bits or at log n bits or log n parts. So you would be able to re-randomize this using PRG that works for these k-wise. And an example of this, also a very celebrated example, is the notion of k-wise uniform bits. So the idea is that it's exactly what I'm saying, but for bits. So like PRGG is k-wise independent if when we sample x uniformly from un, so n uniform bits, and we look at this should be t. So when we look at the sort of the seed length of our PRG, and we look at all the distinct k indices of our inputs our outputs. So whatever we're going to feed to our test set, we want the I bits, the I1 bit of gx, the I2 bit of gx, and so on to look uniform. So look at just these, but like we have some function g that produces a bunch of like sequences of bits, and when we look at just k of them at once, we want that the probability of seeing any of the length k binary strings to be 1/2. So we want them to happen the same. And this we know that from this paper from 85 by along with Tai that there exists such a PRGG with a seed length of k log. And if you think about it, this is much better than the naive thing where if you wanted a PRG, like one possible PRG is like nothing, like take any uniform random bits and produce n random bits. So that will have seed length of n. So if our k is small, then our this PRG will be able to prove these k-wise independent tests with k log n. So this is much better than the alternative this stuff. And here, an interesting fact about this stuff is that think a little bit for those that are familiar with like theory, think a little bit about what's going on here. The setup of pseudorandomness is very similar to a setup where we want to produce, given a message, we want to produce some code with a certain distance. And in fact, this result of along the line type, this construction of PRGG is exactly the same as very famous set of codes called as page codes. So the PRG is you take basically the generated matrix of this a code, and this is your PRG. It takes bits from TC blank T or T plug in and produces figure using this generated matrix. So it's exactly the same thing. There's this parallel between a lot of the results in Paredes where they're usually equivalent to some code, and so there's a lot of interest in studying randomness also from the perspective of a lot of okay, so but the big picture, like kind of message on it as here is that the interesting thing is sometimes we only want to look at functions that look at only a small number of bits of our declarator. And this is the idea of QoS. So here's another notion of QoS independence. So let's say you have some set pi that is maybe a multi-set, not necessarily a set of permutations on n elements. And we're going to call this set k independent. If when we sample pi from lowercase pi from the space multi-set pi uniformly, so we're taking one of these permutations. When you look at the distribution of these pi's, for all distinct k sets of k indices, when we look at the permutation applied to all the indices, it's going to be uniform in n sub k, and by n sub k I mean sets of k distinct in numbers from 0 from 1 to n. So the picture looks something like this. You have all these different permutations on our set pi, and if we only inspect, for example, bits 1 and 2 and 3, and look at the permutation or the small permutation divided this bit or this index and this index, so the second index, and look at all those permutations, they'll look uniform in this set of all possible k strings of length k with elements. So it's kind of what you would expect. One of these permutations is both here. So this is another notion of QoS independence that is very that has been very important. It can lead to a lot of interesting applications. One example of application for this kind of thing is if you were working with, for example, regular graphs, and there's a lot of models of regular graphs that are based on you want to basically set up a lot of vertices and then add a lot of matchings to these vertices, and matchings are kind of like permutations. So if you have some results about uniformly randomly regular graphs and you want to de-randomize that to get deterministic destruction or something, you can sometimes use this QoS. This is something that I've involved in a lot. I've worked with this as well in the past, and this is very popular. But actually, building k-wise independent permutations is a little bit harder than building k-wise independent bits. So what we usually do is we actually talk about approximate dependence. So I'm going to kind of revise this definition, and instead of having k-wise dependence, I'm going to say that something is delta k-wise dependent. If instead of being uniform in this setting, k, it's going to be delta close to uniform. And usually by close we mean in like something little variations. So our distribution over these permutations, we want it to be very close to the uniform distribution over from set 1 to n. And so this notion is it's kind of a weakened version of the previous thing. So delta 0, that's exactly the same as the previous thing I showed you. But now if we can work with a little small error, people have showed there's a couple of results from Kaplan-Mauer and Reingold from 5, and Kasabal 8, that we can construct a PRGG. So in this case, like a set of permutations pi, where the C length is something like k log n plus log 1. So very similar to what we have before bits, but now you have this extra 1 over that log 1 over delta error. We can't actually convert just because of the nature of it. Sorry. So for the exact question, what we know is if you have a delta k-wise set of delta k-wise, you can construct a family of permutations that is very close in distance, something like n to the k. If delta is like something like n to the constant times k, close to a set that is k-wise. So here, instead of being like every single permutation is delta close to uniform, the whole distribution is very close to a distribution that is k-wise independent. I think this is the best thing to know, and this is often good enough to use for a lot of where you, because you know that this distribution is going to be very close to being k-wise independent, you can use that fact instead of k-wise independence, and you'll have an extra error that you can put, for some application.
That's the real reason why it's like 0.
Good question. I think there's some lower bounds. I'm not entirely sure how they work, but I think we don't expect to be better than. Sorry, that we don't expect to be able to improve this a lot more. I honestly don't really know. I know that there's some results. Lower bounds, but okay, so at this point, I think I'm going to just stop for like a second, see questions. What I've been talking about so far is kind of the review of a lot of the past several years, and I'm going to tell a little bit about stuff. So, like I said, the big picture, like what we want to take from what I've said so far is that if we want to prove functions that only look at x or k elements of our input at the time, then we've been able to do that for certain types of objects like permutations. And what we were trying to do is kind of extend the solution to more kind of more options. And that's why the talk was called delta k or independent or pseudorandom rotations. Second, so here's a new definition, and this definition might be hard to parse up step by step, and I show an example. So now let's suppose that we start with a subgroup of the general union. So Gn is some subgroup. You can think about Gn as the problem or the unitary group, but for now let's just. So we call distribution D a delta approximate T design for this group. If for all polynomials P that take entries of so these are matrices that take entries of the matrix and map it to a real number, such that the degree of the polynomial is equal to k, and the sum of the coefficients of the polynomial is equal to 1. Then we want the following to be true when we take the expectation of the polynomial applied to the random matrix sampled from uniformly from all the, for example, matrices, and we compare it to sampling from our distribution D. We want the distance between these two matrices to be something like delta over n. And I'll explain a little bit why delta here. But here's an example. So, for example, our polynomial P might take like 2 by 2 matrix, and this would be an orthogonal matrix, or something like that. And you could do something like, take the first the 1 1 entry of this matrix square and multiply by entry, and then scale this by 1 point. And then also to take the 1 2 entry and multiply by next 1 squared, and then scale it by 9. So this is a polynomial of these entries, and the sum of the coefficients is 1. And the degree of each of the this polynomial is so this is this is the type of polynomial that we consider. And if for any of this polynomial pool all of these types of polynomials, and for distribution polynomials, then we call this a delta approximate. And so a little motivation why we care about this method. So for example, one group that you'll be able to plot here instead of group is the symmetric. So permutations or permutations. So if you decide to care about permutations and you want to kind of run this result, you will recover exactly the previous result, or rather the previous definition that I used. Definition of delta k-wise. But the difference is you have like this delta over next to k. And this is just a difference about forms, or like distances that we care about. Here, we're looking at so our polynomials that take a polynomial matrix and not real. Our polynomials are going to be something like look at certain things of our permutation matrix and do something with it, which is equivalent to saying something like if we look at a certain entry of our matrix, if this is a permutation matrix, looking at that entry and expecting it is the same as saying is the third index of our permutation 5 or 3 or something. It's like an indicator function for like whether or not a certain element. So this is what these polynomials are doing. They're expecting just at most k elements of our time, which is but now we have this weird, distance based on this expectation. The expectation of for any possible kind of function or test that we do on this permutation by looking at just k of these positions, we want the expectation of the taking this test on our pseudorandom distribution to be close to the expectation of this test on a purely uniform distribution. And you want this distance to be small, but previously for the delta k y independence. But in computations, I talked about closeness in total variation distance, but that's a little bit stronger in the sense this is like for every possible, polynomial or every possible function, we have this distance. So if you want to convert this into a delta to a total variation distance, you have to normalize or normalize. That's why it gets and over it. If this doesn't make a lot of sense, don't worry too much about it. It's just detail, but if the support of D, yeah, it has to be supported on G. So we want to take like the for example, what about this? We're gonna construct a set of matrices, so a finite set of matrices, where like previously for permutations you got a set of permutations, and now I'm going to give you a set of matrices where if you choose a matrix from this set on the random, you'll have this problem.
So if G is the permutation matrix, this position is stronger or the same?
It's a good question. I think it's slightly stronger, slightly weaker. Question is, but I think this is I think this is slightly stronger because it's like if you want to remember this definition, it's like you want to look at all possible. It's like you have to kind of union bound of all the possible like sets of n or like sets of n the L K elements like on K, and you kind of union bound of all of them. But they're like basically equivalent. Especially in terms of like applicability, this kind of thing. So I'm not sure about that. What I know is that like what I've told you so far kind of this is just definition. Kind of let this definition whatever it wants. Think that I'm gonna like treat like results okay are not like this generic, like we don't obtain this all possible we'll only obtain it for like specific types of groups that look like. So if you want to think more complicated other like groups that are not necessarily classical groups, things will get even more. And one kind of key aspect about this is the representation. I'm not going to talk more about that, but one of the way that we set up some of our groups, we has representation groups. And if the representations are not known or kind of complicated, that's a good question. Maybe something. Honestly, my kind of knowledge of is kind of limited to some of the things here, so I'm not sure exactly.
Because it makes sense to us, but and we
But it does, yeah.
But I think that's you say.
So I can't hear.
But are you going to
Oh yeah, so I think good point. I mean, kind of adding some details. So the speed for measure here is the hard measure on the we care about, like so the hard measure for the orthogonal group or the hard measure for unitary group or something like that. I'm trying to like kind of find these details, even though they're obviously important, but that's the measure here. So let me quickly, like, let me just quickly kind of tell you what types of groups we like to use in this setup. So we're gonna show this for three types of three groups. So the orthogonal group, the unitary group, and the symmetric group. Symmetric group is what I just mentioned, but it kind of covers the case. The orthogonal group, this is kind of rotations. This is the rotation, so we can think about it as we are rotating something and only looking at the local part of our rotation. And that's why I call it topic of superrotations. And you might ask, why do we care about this? Why do we want to like have superrotations? One example of that is if you want to de-randomize algorithms that require things like hyperplane family, which is, for example, classic max cuts, opposite result where you put some max, so instead of STP, and now you have a bunch of vectors, and you need to make some binary precision, and you pick a random hyperplane to kind of split your points, and then you pick all the vectors in one side have ones and the other have ones and zeros, and you kind of pick a max cut like this. If you want to de-randomize results like this, use this kind of rounding where you need like a separating hyperplane, random hyperplanes. This you need to pick kind of a random rotation. So there's this result by Gothari and Mecca, which was actually inspiration for our paper from 2015, where they show how to do these like pseudo-random generated spherical caps. So exactly this example that I'm talking about, where you have some vectors like n-dimensional sphere, and you want to kind of partition them by picking the random. And one of the tools that they need for the result to work is these approximate k-designs for the orthogonal group. And that's why we one direct application of this is that you can randomize efficiently these types of algorithms where you have to do some rounding based on randomizing. And the other group that we also are able to show things about is the unitary. I like to think about this as quantum rotations. I know this is probably not very like kind of informal thing, but the reason I think about this as quantum rotations is because these are kind of rotations in the complex numbers, or the set of complex numbers. And it's not as clear why we should like care about like things like complex rotations. But one example is because these unitary matrices kind of define quantum gates. People actually care a lot about designing like pseudo-random, random or like pseudo-random uniform unitary matrices because they kind of define like pseudo-random quantum circuits. So if you want to kind of like sample the quantum gate at random to kind of somehow, then they construct a circuit, a quantum circuit of gates that is pseudo-random or as close as random as possible. This is something that you care about for multiple reasons. One of them, I actually have no idea why, but this is for a reason called ADS CFT conjecture, or theory, which is some conformal field theory physics that goes to black holes. I'm not a physicist, so I have no idea what like mean. I just think it's related. Another one that is more maybe related for scientists in the audience is quantum supremacy. So there was this paper from like a couple of years ago by Google where they were like, claiming to have achieved quantum supremacy. And one of the key things that they have to do kind of set up with quantum supremacy result is they need to kind of sample or a random quantum circuit. And to sample a random quantum circuit, you need to you need some pseudo-random generator. You can't just sample it you can't just sample uniformly unitary. Since the matrices are it's not even clear how to start. Like for permutations, you can just have a set of all permutations set uniformly, but you can't have the set of all unitary. These types of results in one point. And even though we didn't actually do this for like actually carry out all the groups for like other groups, we think we can also use this for things like the symbiotic group. No, for GLN, I don't think you can use this for that. It's you kind of need this property of rotations, like that rotation variance is an important property that we need for the report. And so we don't really have a lot of kind of the setup we do, at least in one part. I want to talk a bit more about the proof or like the construction steps. One of the steps, like I think, works for kind of a matrix that is any subgroup of GLN, including GLN, but the other part is a little bit more complicated. How to use rotational invariances. Oh, good question. Good question. I think so, but again, it's more work because now like the representation is quite different, and like for this step where we have to work with representation theory, if the representations kind of get crazy, you have to like do more work. But as long as they are not too crazy, like, I believe you can also do that. So you could potentially have this for, the orthogonal group over the reals, the special orthogonal group is the unitary group, the special unitary group over the reals or the complex numbers, or you can also have the orthogonal group over the complex numbers, all these variations. We focused on like just the ones that were kind of have had some at least some applications that we but potentially you can extend this. Plugging in the right, like changing like kind of one of the steps of our group to instead of using the representation of the unitary group, you want to use the ones of special. As long as they have rotation, that's a good part.
So in this definition, where we have operation in front of that.
Yes.
But it's still, because that's not necessarily how, for example, the rotation is not an L1. How it should look like it should be allowed.
Can you say if you want to add a.
So instead of M from D, I take M times something.
Oh, I see. Okay.
So somehow it feels like it should allow it.
Should allow that.
Because the normal one.
I'm not sure. Like usually it should.
So D. Oh.
Yeah, D. Yeah. Like, for here it is invariant, so that's like.
But for D,
I'm not sure.
D somehow you're fixing direction.
Yeah. It's a good question. I have to think a little bit about that. I'm not sure. But that's a very good question. I think you should be able to do something like that, but I don't think it will follow naturally from what we have. Okay. Any more questions? So far, lots of So I'm not gonna have a lot of time to like go over the proofs, but I still want to give you a little taste of how that works. And so we're going to focus on the orthogonal group now by kind of our discussion. This was our main motivation, so we actually started by just with the orthogonal group, then realized that we can actually set this. So it's kind of like we're going to show you kind of what we actually like did. It gives a general framework that we are. So now I'm just showing you the exact same definition before. So like delta approximate design, some polynomials from the group to R, where the degree of the polynomial is k and the norm is 1, and we're looking at this expectation of like either like a uniform random matrix polynomial, or you want that the sample from D and you want this to be small. This is small. So the first thing you should observe is that you can actually replace this by a very similar thing. The polynomials I have now, I just have for monomials alpha from the same thing. So these are monomials from entries of the orthogonal group R, the degree is at most k, and I have the same thing here. The thing about this is the previous definition follows this naturally just by using triangle inequality. Since for any, if you write a polynomial, you just polynomials and have this result, you can kind of apply it. So we now will only focus on so monomials, we're just looking at, monomials of degree at most k means we're looking at most k entries of our matrix and kind of multiplying. So now here's something that I really like to do in all my research. This is kind of one of my favorite things about what I do is you start with this umbrella that looks like either combinatorial, algebraic, or something, and there's always a spectral field. I always like to convert problems into some spectral lens. And that's what I'm going to like to do right now. So I'm going to start by defining this thing called representation. It kind of sounds like complicated, but the only thing you know is that given some value k, the tensor representation of some matrix G, like so G can be like any matrix before. But again, we're not just here, just going to focus on the so G is some orthogonal matrix. So the k tensor representation of the G is just G tensor k. So we take the matrix and we tensor it with itself. It's the normal tensor product or the parameter product. And so, and here's why I'm defining this thing. So if you have for monomials like before, let's say the thing before, if you have something like polynomials from the orthogonal group to R, we would get this k, and you're gonna like study kind of this distance sampling from or pseudo-random distribution of the group. If we instead of replace this is good, if instead of using it and actually bound this by the kind of the max norm, so by max norm here I just like create the biggest element in this matrix of tensor representation of M with some E is tensor representation of group, and then you further can like bound this by group. And so why can you do this? And all this seems like kind of like crazy and complicated, but the reason is very simple. Is that alpha of M, so like any monomial alpha of the entries of the matrix M. This is going to be an entry of the like bigger matrix where we take M and tensor product k times. The reason is if you start with something like this, so we have this, let's say that M is like a matrix that has M1, 1, 2, 2, 1 entries. Let's say that our monomial looks like it's a unique monomial that looks like the diagonal, multiplies the diagonal. So if you now investigate the tensor product of M itself, this is the same as M11 times M, M1 M, and you kind of blow up these matrices. So if you think about this element over here contains one of the elements of this submatrix over here is M11 and M2. And so for any monomial you think about, it will be one of the entries of this big matrix. And if you care about monomials of degree 3, then you can do this 3 times, you blow up this technique more, and we'll have one entry that will correspond to. So instead of bounding monomials like this, like we can just bound the total matrix, the maximum norm of this matrix, and we'll do that by bounding the norm, so that the largest eigenvalue the largest single value of the matrix. And if we can bound this, then we also bound this. So now we are going to focus on just these tensors instead of the additional. So now here's our framework. We'll look a little complicated, so I'll accept it a little bit. So our framework will have 2 steps to kind of construct these pseudo-random. The first thing is we're going to construct some set M, the matrices in the opponent. So finite set, we wanted to have small sets, such that when we look at that, the same thing that we had before, so it's this operator on distance between this clear tensor representation between the distribution. So when we sample M uniformly for the 70%, and then when we sample it from the all or R measure from the uniform measure from the group, we want it to be at most 1 minus 1 over polynomial. So you can think about this as this is basically not like the worst non-trivial gap. So if you get something that is like anything best than trivial, and 1 is the trivial gap is 1 because, for example, if you pick M to be M to be 0, so like there's no matrix side, the 0, the empty set, there's no matrix in the set, This is just going to be operated on the same right. And I'll show you why in a second, but this is the projector matrix. So the large eigenvalue is 1, so this is going to be bound up. You don't do that. If you do nothing, you have like around 1, which is fine. But if you do anything that gets you like anything better than 1, so like any like non-trivial gap, so gap, by gap I mean like 1 minus, then this is the we're going to be happy. Even though we need something much better. One like a really small error, then that's just not. And we're going to try to construct something like this where the size of our set n is relatively small. So like polylog, polylog. So the seed length, we have a set of polylog with like polylog n matrices. The seed length is log log. So for example, from this set, we need to give a seed length log log n random fix so that we can pick an element of this set. So we have a very good, like, our seed length is amazing, but our error is good. This is the first step of our framework. Now, our second step is we're going to reduce this error. So we're going to use this set n to obtain a better one in paths, where the distance is much better, it's the delta that we care about. And the set of our n is going to be polynomially log x favor delta, which means when you take the log of this, the seed length of this is just this is what we care, exactly what we have for k log n plus log 1 over delta. You might protest and say, wait, I thought you needed delta for n to k. But if you kind of plug, if you have this, and you plug delta over n to k here, because we're taking log of 1 over delta, you still have the same. So I'm kind of cheating a little bit here, but the point is that if you just take this, you also get the. So our framework will do two things. First, establish a graph, and then take that and reduce the error to get a better distribution with an optimal error, but still not too big in size. And this is what we do, and I'm going to kind of show you how to do this. And this is the same framework that was used, for example, for the Western result, but that was very specific to mutations. What we do is kind of generalize the tools that they use in order to be, it's not just for communication, also you have to do a lot of that, but you also have to do a lot of work to set up this function here, because it's much more complicated. So I'm going to just very briefly tell a little bit about how this works. Okay. So I'm going to actually start with the second step, reducing the error, because I think it's more straightforward. And this step is actually related to some topic was given by Fernando. I'll explain why in a little bit, but what we're doing is kind of similar to who's been that topic. So let's recall our goal. Like, there's a lot of numbers here. This is the exact slide as before. We were given some matrix, some set of matrices n that has this like hash property that has the number of gap, and it's a small n. And we want to construct this bigger n paths that has a really good error and still not too big. So here's the intuition to so let's forget about matrices per second. Let's say you have an algorithm that has success rate of points. So like you give it some like random points, you like throw some random points, get some random bits, your algorithm works probably. If you want to boost this success probability, you want it to be really big, do the natural thing, you kind of like repeat the algorithm with new random points a bunch of times, and eventually it's like 1 minus 7. So you kind of repeat your algorithm. The intuition is the same thing. So for example, for permutations, let's say you will have start with a set of cards, and you want to shuffle these cards, and you have some very basic way of shuffling cards, which might be, you throw 2 dice, and you look at the numbers of the dice, and you switch those up. So like you pick a random transposition, and you like apply. So if you repeat this a lot, like if you keep applying the same, like sample if you want, you apply, apply. If you do this enough times, it will converge to uniform. So it will eventually be a uniform. But the question is how many samples you need in alpha. But now for our setup, it's the same thing. So our m hat is going to be something like you're going to take t powers of n. So you're going to take all possible products of t matrices from our setup. So for mi and m, you take m1 times m2 and so on to n t. So that product of matrices, and you take all the possible products. And now I want to mention that, and I'm going to prove this part, that if you do this, you boost the error by reduce the error by 1. So if you have initial set of matrix n that has an error of epsilon, if you take this t matrix iteration of t power of the matrices, your error is going to be epsilon. So your error is going to go down. And the proof is very simple. I'm going to show you the proof. I think that's interesting. The first thing is, let's multiply to sort of this quantity that we're using a lot. This is just the expectation over the orthogonal group of our representation. So this is kind of like, think about this as how good is taking uniformly random orthogonal. And the key thing is that this is a projector matrix. Like I mentioned before, there's the fact that there's some rotation variance. So to show this, so the idea is that, okay, if you take any matrix A, if you take any matrix M, we have that the pi multiplied by the k tensor of M is always equal to pi. And this follows from rotation variance. So like the idea is that if you have, like Mark was saying, if you have some rotation, some rotation and dimensions, and you now apply a perfectly random rotation, you rotate this arbitrarily at random, uniform at random, you still have uniform rotation. It doesn't matter where you start if you apply uniform rotation. So because of that, this is a projector matrix in the sense that if you start with any matrix, any rotation, you still get the same. So this is the definition of the matrix. So that's finding by this class of matrix. So now, like if we look at the following objects, and this gap between this is the thing you care about. So we have our n matrices, and you can interpret this as how good is sampling from like m, and you subtract it to pi. How good it is to sample from. Take the power of this. This is going to be equal to this because all the cross terms will basically cancel. They're all going to be equal to pi. And so at the end, you get something that looks like all the cross terms will be canceled because whenever you have something times pi, that's just pi. And then, so we care, like now we have that this thing is equal to an expectation of the t power of this expectation. Think a little bit about this. This is the same as the expectation of that. We're now just taking like these products of like these matrices, and so this is given by the and then the final kind of like step of the proof is to just observe that the eigenvalue, like this thing over here, is what we care about. It's kind of a matrix over here. And these are matrices. We're taking expectation of the distribution of matrices, so there's all this matrix. So we care about this matrix, and the eigenvalues of this first term are the t powers of the eigenvalues of the inner. So the eigenvalues of the whole term are the t powers of the eigenvalues in this. And so, in particular, because the operator over the eigenvalues, this means that if we have a value of epsilon, for the inner term, we have a value of epsilon. I'm going a little quick here, but the idea is just the fact that we're looking at powers of eigenvalues. And so this shows the level I did before. So now the idea is that if you pick appropriate t, like if you pick t like this, log n, k, log 1 delta, you can prove that this thing is like this is going to be acceptable. So you have to just pick the appropriate. The issue is that if you do this, the steep length is actually it's now the size of n hat is the size of n to the power of t. And this t is really big, So the seed length is like poly log n k log. You wanted k log n plus log of 1 over delta, not poly. So it's going to be like a new. This is a decent reduction. You get good error, but the length is good. And so the intuition to get a better reduction, mention it very quickly. Instead of doing like all of these different products of like key matrices, you're going to just take a subset of those products. So let's say you start with a gene expander graph, and if you don't know the definition of an expander graph, the only thing you have to know about it is that this is a sparse graph. So like this is a deregular graph. And now you're going to take this. We want it to have the exact same number of vertices as our set n. So we label each vertex of our graph with its names. So this is the picture. We have our graph G. It's regular, so every vertex has the neighbors, and you label each one of them with like one matrix count, like one unique matrix. And then now we take this expander product. So instead of taking all possible products of the matrices, we take products where of like the V and V1 and V2 and so on. If they form a walk in. So if V1 is connected to V1 plus 1, and so V1 connected to V2, V2 to V3, and so on. So take a random walk here, or like the walk of T, and these walks will define the new matrix. Note that now, like the size of n instead of being n to the t is just going to be equal to n times the degree of our graph. Because at each step we only multiply by d instead of multiplying. Now there's two challenges to make this work. You need to show that this reduces the gap. So like matrix information. And then you have to pick the appropriate expander graph. And this is actually a little bit more complicated than what I'm showing. You have to actually pick a lot of expander graphs and not just one. But the idea is kind of the same. But these are the two challenges to solve. If you do, you get this like big technical results that I don't expect you kind of look at very carefully. I just kind of wanted to show you how it looks like. But all the kind of things that we talked about are there. Like you're looking at this gap between like m and you know, like you have a non-trivial gap between m and pi. You have some algorithm that kind of like combines these by like picking like the appropriate expanders to get a new m hat that. The translation is that you get the exact one. By picking an appropriate like length, all the like appropriate lengths of these box, you get a final m hat with the seed length we care about, a log n plus log delta, and the so this is the key result is that we show this thing, and this operator reduction result is very similar to the results that operator. We kind of had this. This was independently. I think Fernando's result is a little stronger because we were interested in a slightly different context, but in our result we're focused on this matrix case, and we only care about values. So the key thing that I want you to take in mind is that we're going to just go back to the slide. Is that we're reducing. When you know the t powers of something work, you want to reduce those to taking expander walk, like walks on appropriately chosen graph, and the graph being taking expander. And kind of the motivation to picking expanders is that expanders have small or large spectral gaps, and we kind of care about spectral gaps. This is kind of like the motivation to like thinking about expanders here, and kind of works, but this is. Okay. I don't have a lot of time, so I just want to like kind of very quickly mention that part. So this is just you need to still start with like something has an gap, and you can reduce that all the way to like paramount. But you still need to show like if we can construct a matrix set of matrices that has this property, and this actually like takes a lot of effort. There's a lot of technical details to it that I'm not talk about. And the technical detail where like we need to assume that n is a power of 2 in order for this setup to work. You can also kind of do this for powers of primes by doing the same proof, but that's slightly different. But usually, like power of 2 is good. And the idea is that actually going to kind of skip through this very quickly. You can ignore the first part of the slide because I'm getting time. But the idea is that you start with a universal set in our group open. So universal set is, for example, in quantum, if you have a set of gates, where you can basically use those gates to construct any possible so in mathematical terms, if you have a set of matrices such that given any matrix, you can there's an arbitrary little, maybe a very long product of these matrices that or like a sequence of products of these matrices that gets closer and closer and kind of converges to the any matrix. So it's kind of dense. It's a set that is dense in the set of all matrices. So you start by doing something like that, and then you basically for like a small n0. So like you start like something like that, small positive, and then you kind of do something like you want to kind of apply this locally to like a bunch of places, and so you sample the places that you're gonna like apply that to only random, and you apply it to all. And again, this might not mean a lot, much because going through this. But the idea is that using the kind of the intuition from quantum, where you like think about your state as kind of a product of states, you use something like this, where you take your universal set and you kind of apply it to different substates of your final state, and you take the substates you apply to each one. And if you do this, we show that you get this count. And very quickly, the idea is that we first have to use some results, some recent results by Morgan and Gember and by Paredes and this XR to show that if you have something, you have universal sets. This also this is kind of like almost as good. Think about this as basically being almost as good in terms of our this like operator role that we talked about, as taking instead of taking a universal set, take uniformly random like small problem matrix, same procedure. And then we kind of like induct by like showing, oh, like if you do this for n0 bits, this is almost as good as we like have a sampling a slightly bigger orthogonal matrix and sampling a little more bits, and you kind of like iterate to this until you get a bunch of like bounds on each one of these things, and then you kind of show that these bounds. I know that this means nothing because I'm not talking about the details, but the main point here is that you kind of like progressively show that you can, instead of sampling like n0 bits, you can now consider or n0 such states, you can sample +1 and n0 +2 with a small loss. And we show at the end that the losses don't end up twice. And you have to use a lot of tools here in order to like analyze all these things. This is where the representation comes up, because you have to analyze how like these things kind of compare to each other when you have like one bits on one more substate. Okay, so I know I didn't explain this very well, but I just kind of the idea is that you kind of start the universal set and then progressively apply it to them. Yeah, so I want to just flash the very first slide to kind of summarize what we talked about. Hopefully, I convinced you that pseudorandom is a thing and boundary independence is a concept. Our framework of pseudorandom rotations is applicable to all these types of results we already have. So we need to like sample something that looks like a rotation, or a spherical cap rotation, or a quantum circuit, or something like that. And the main two things of proof is you need to set up some non-trivial gap by doing something, and then reduce the error of that by kind of boosting it. And that's it. Thank you. Yeah. Sounds good. Yeah, thank you very much for coming.